We are delighted today to have this special colloquium as part of the fractionated quantum matter meeting. It's a particular pleasure to welcome Duncan Haldane back again to ICTS for this meeting and for agreeing to give the special colloquium. I don't think we need to spend too much time on introducing Duncan, but for the sake of form. Duncan Haldane is the Eugene Higgins Professor of Physics at Princeton University and the recipient of the 2016 Nobel Prize in Physics for theoretical discoveries of topological phase transitions and topological phases of matter. He received his Ph.D. in physics from the University of Cambridge in 1978 and with Phil Anderson. And in fact, I think there's a sort of a lineage of 3 Nobel Prizes, Phil Anderson and his advisor, Van Vleck. And so it puts a lot of pressure on Srinivas. So anyway, so prior to Princeton, he held a number of positions at the Institut Laue-Langevin in France, the University of Southern California, the University of California, San Diego, etc. Of course, Professor Haldane's contributions in a number of different areas have been very seminal, very original, and we'll hear some of that in the course of this talk in the context of spin systems, topological quantum states of matter, and entanglement spectra, etc. In the morning, he talked about the fractional quantum Hall effect, etc. He's, of course, has numerous recognitions apart from the Nobel Prize, including the Fellow of the APS, the American Academy of Arts and Sciences, National Academy of Sciences, the Royal Society, etc. And has also received the Dirac Medal of the ICTP and the Oliver Buckley Prize from the APS, and so on, but I will not go into any more detail into that. So let me welcome Duncan to give this talk on unexpected surprises. Before that, I'd like to invite Professor H.R. Krishnamurthy to come and just give a memento on behalf of ICTS to Professor Haldane. Yeah, but we don't want, it's a small mug from ICTS.
Okay, thank you. So this is, since it turned out I'd already given my standard talk here, this is a different one. It's more personal, and it's really, except at the beginning, it's really a story about, you know, what led up to the things that I got a Nobel Prize for, and you know, hopefully it'll be inspirational for others to, you know, take guidance from it or otherwise. So, okay, unexpected surprises. It turns out all the best things that one discovers are unexpected because there's plenty of smart people out there. And if people know something is there to be found, like there's some treasure on a particular beach, there'll be 500 people all digging furiously at their holes trying to find the treasure. So your actual chance of finding something is really not participating in that kind of treasure hunt, but by good luck, by accidentally your research progress, happens to take you past a place where there's some treasure that's buried that no one knows about, and you happen to be looking and studying your environment carefully enough when you kind of kick a bit of a rock out and it exposes the treasure. And it'll probably only be a little tiny piece of it poking about, so you have had to develop the training or something to be able to spot something that's significant. But in any case, anyone has the possible chance, I think, of finding that. Okay, so around about 1980, two kind of, condensed matter people thought they knew everything. You know, there was a whole series of superconductivity, phase transitions, magnetism, Landau theory. But two things actually discovered very close geographically to each other. These discoveries both happened in Grenoble, France. One was the von Klitzing discovered the fractional quantum Hall, the integer quantum Hall effect as a huge surprise, and a much more kind of more obscure thing, something in magnetism happens theoretically in a nearby laboratory, all about the same time actually. And they turn out to be things where quantum entanglement in some sense or other plays a role. Anyway, they were topological, which no one really thought about at those times for topological quantum states. So they were kind of surprising. So let's first quickly deal with von Klitzing. So, of course, there is a big discovery, and it's now replaced the international system of units. We're now measuring, our kilogram is now measured with the Kibble balance, which uses quantum Hall effect and the Josephson effect, I guess, to get E out of E squared over H and E over H. But anyways, this is kind of democratized weights. French imperialism was imposed the kilogram on us, but you had to go to Paris to compare your street traders' weighing scales to the French official kilogram if you really wanted to prove he was swindling his customers, right? So now you can do it with quantum mechanics. Okay, the quantum Hall effect discovery was luck, as we'll just see, and it was a luck in the choice of an experimental protocol. The same experiment had been done earlier by Japanese researchers. They used a slightly different protocol and found nothing. Von Klitzing didn't anticipate finding what he'd found, but the protocol he'd chosen made it immediately obvious to him. And so that's really an example of the unexpected luck, or the luck that takes you to something unexpected. So the Japanese protocol was quite simple. You've got a big magnet, and you've got a quantum Hall bar, and you want to measure how the current, the Hall voltage as a response to a longitudinal current flowing down the Hall bar as a function of B or something. The Japanese protocol was switch on the field, get your nice magnetic field kind of very kind of accurate and clean, then put your Hall bar in, switch on the current, switch off the current, switch on the current, take another measurement, etc. Each time you switch on the current, you never get exactly the same current. The field wasn't changing, but the current was approximately the same each time, but it wasn't enough to show up the remarkable thing that von Klitzing found. Von Klitzing's one was slightly different. He had his Hall bar with a constant current generator current across it, and he did his measurements by switching on and off the magnetic field. You never get exactly the same magnetic field each time you switch it on. It turns out that didn't matter because of the Hall voltage current relation does not depend on the magnetic field, at least within some range of magnetic fields. The current in the Hall bar was unchanged each time, and the Hall voltage came out to 5 significant figures on his voltmeter. Of course, he probably initially suspected a faulty voltmeter, but no, the voltmeter was working properly. He found this amazing precision, which is now 10 places of decimals or something, and found a new effect. And a Nobel Prize followed very quickly in this case because it was immediately obvious how important and useful it was. And the quantum Hall effect is actually topological. It took some time for it to become clear. And the basic topology is in the counter-propagating edge states, which are always, and those are, the fact that they have unusual edge states is a very typical feature of topological materials. And the key thing was these edge states pin the Fermi level. So the original samples were, the original thing viewed a dirty sample, which is really true, but you don't need a dirty sample. So long as the ratio of the perimeter to the boundary is not 0, then you'll have some plateaus in which the magnetic field, where you can pin the Fermi level, so it doesn't quite matter what the magnetic field is, so long as it puts you in that ratio. And in fact, the crucial thing in the quantum Hall effect, the topology, is these chiral edge states, which allow spectral flow of states to flow in and out of the system. And I talked about that this morning, so I won't go into that. But anyway, it's a remarkable thing. And the most remarkable property of quantum Hall is actually what's now called the Strader relation, that rather than the current being strictly having a quantized relation to electric field, it's actually how changes in the electronic charge density have a quantized relation to changes in the magnetic flux density, which in some sense is the true quantum Hall effect, and is the first one can be obtained for the second one by taking a time derivative and then an integration. Okay, so that was an amazing discovery, and it was made partly by luck in choosing that. It probably would have been made in the future because it's, you know, there's not too many ways to do this experiment, but it was really, it could have been found about 3 or 4 years earlier if the Japanese work had used a different protocol. Okay, the second surprise is this one, which is with my little story. And okay, it's actually, my original derivation of this and discovery of this is closely related to Kosterlitz-Thouless, who shared the Nobel Prize with me on this. And it's actually the quantum version of Kosterlitz-Thouless, where Kosterlitz-Thouless is a topological phase transition at finite temperature in 2 spatial dimensions. And there's a famous way called Wick rotation, where you can convert a classical statistical mechanical problem at finite temperature in d spatial dimensions to 1 in d minus 1. So this is it's a one-dimensional problem. Okay, so when scientific trajectory is actually rather random, and especially as a graduate student, it's determined by things which are mostly outside your control. And you have to sometimes make decisions, and it's not clearly obvious what the right one to do is, and you don't understand what the significance will be. I mean, it's like multi-worlds, you know, many worlds quantum mechanics or something. So in 1973, after finishing a 3-year undergraduate degree, I think they use 4 now, at Cambridge University, I had the chance to stay on, and I was offered the opportunity to work with either Phil Anderson or condensed matter, or Michael Green, who was one of the founders of string theory. So Mike Green told me about massless, I remember this, massless rotating relativistic strings, which were a model for the hadrons. And they were possibly related to the MIT bag model, which I imagine was quarks with in there. It seemed really intriguing. But finally, I thought the condensed matter seemed more concrete. I'd had a class at Cambridge in my final year called Advanced Quantum Mechanics. Since Phil Anderson only had a half-year appointment, I think he had to leave halfway through. So the second half was done by Michael Green. So both halves were very interesting. Michael Green taught Dirac equation. I can't quite remember what Phil taught. But before that, we'd had all these rather tedious classes about, you know, scattering theory, optical theorem by particle experimentalists, basically exercises in the O3 rotation group or something like that. So these were a breath of fresh air to hear these kind of interesting talks. But in the end, I went with Phil. And of course, this was string theory of the hadrons. About 6 months later, the MIT bag model collapsed, and then string theory went into what they refer to as the wilderness years, where exactly 2 people, Mike Green and John Schwartz, were working on it until it was resurrected by Polyakov and then Witten. So I'd have been dead, basically, career-wise. So I wouldn't be here if I'd made that decision to work on string theory of the hadrons. Okay. So Phil Anderson gave me a reprint of his Lesuche lectures on the Kondo model. He'd just been working on the renormalization group of the Kondo model and finished his so-called Pullman's renormalization method after his earlier kind of path integral method. And he told me to think about generalizing all this stuff to include valence fluctuations, because there was a topic very popular at the time called mixed valence materials, samarium hexaboride or cerium metal, where the ion sometimes is a bit kind of bipolar about what valence it wants to have. So then, of course, Phil, having a part-year appointment, left for the US, and there I was with the reprint lectures of Les Houches. And I spent the next 6 months trying to understand whether the d orbital in this model, which was actually part of the conduction band or the valence band. So I was only other people for guidance were people doing band structure theory. So of course I tried to get them to help me. So what's the Kondo problem? It was kind of a big problem at the time. We'd now call it a quantum critical point. It's a problem of a spin coupled to a metal. There's this exchange coupling, S dot S. And the thing is, in perturbation theory on this, it's all kinds of logarithmic divergences blow up as you go, as the temperature goes down to zero, because we have this quantum critical point. And basically, for the negative sign of the coupling, the spin, the ground state, the ground state is a state where the spin is decoupled from the metal. Well, for the positive sign, the spin kind of dissolves away and is kind of incorporated into the metal. And as I say, Anderson, Yuval, and Heyman had probably the earliest renormalization group treatment in condensed matter, which resolved this. Okay. So in the Kondo model, only the spin fluctuates. I'm telling you this because there's some point to this later. In there actually, including valence fluctuations, you have to include charge fluctuations. And there was a model which two variants. So one is the Anderson model, where I've got this so-called d orbital, and 2 electrons in the d orbital have an interaction energy U. So this is like a one-side version of what Phil Anderson at that time was calling the so-called Hubbard model, because I guess he felt some kind of ownership based on this, but he has enough models named after his name anyway. So, and the other version is the Wolf model, the same guy in Schrieffer-Wolf transformation. And this it's actually similarly a model with a single orbital in which there's an interaction U between the electrons coupled to all the other electron states are non-interacting, except this one is part of the metal, and this one has a hopping matrix element into the metal. And so this one, the d orbital, is not part of the Ks, and this one, the d orbital, is a linear combination of the Ks. Okay, so I was kind of scratching my head about this for 6 months, basically. So Phil Anderson had a unique mentoring style. So through his Les Houches lecture notes, I learned about this Nozières de Domenici's treatment of the X-ray edge problem, which was the basis of his initial kind of path integral based Anderson, Yuval, Heyman renormalization group treatment of Kondo, which actually is a pretty important piece of work because it's essentially the basis of the Kosterlitz-Thouless paper. They adapted to do the scaling theory of the XY model. They basically adapted the Anderson, Yuval, Heyman treatment of the X-ray of the Kondo problem. And then I learned there was this is kind of rather complicated, the Anderson, the Nozières de Domenici's treatment. X-ray edge is a kind of quench. And the Schotter and Schotter had a version using a very early version of what we now call bosonization, which was much simpler and treated at least the weak coupling. It reproduced the weak coupling limit of the fancy Nozières de Domenici thing. So I was kind of interested in that at the time too. So when I went with Phil for mentoring, when I would go to see him, I wouldn't actually get advice about my problem because he'd tell me about everything that he was thinking about that day. But actually, that was an incredibly valuable education for me. It kind of taught me how to think and how to. His idea was that to remove all the irrelevant details for the problem, to simplify until either you threw the physics away and you knew you had to go back a step because that's where it was, or you got rid of all the kind of stuff that kind of clouds your vision and sends you off on wild goose chases. So kind of I don't know, I mean, if Sri Raghu can tell you what my style was, I suppose, but anyway, that was very useful for me. Okay, soon after I had an unexpected kind of life and career changing event because Phil Anderson basically had a quarrel with the Cavendish professor, Brian Pippard, because the earlier one, Merrill Mott, had brought into Cambridge, but Pipard was sort of different. And he switched his appointment from 50% Cambridge, 50% Bell Labs to 50% Princeton. So anyhow, so there I was. So I got a NATO, you had to go to Princeton, I had to pay fees. So I got a NATO studentship to pay my student fees at Princeton as a visiting student. And then I got this rather strange flight to the United States. Phil Anderson had an Air Force Office of Scientific Research grant, and I could get a $50 flight on a US Air Force flight from Mildenhall Air Force Base near Cambridge to McGuire Air Force Base near Princeton, New Jersey. Kind of sort of strange, but it turned out to be a life-changing event because that flight was basically turned out to be my exit from the UK. So actually, these are kind of issues that probably people here face. I mean, once you go abroad, especially if you start putting your roots down in some place and live there long enough, it's actually quite difficult to go back home. So you guys actually have to think carefully about what your life plan is. When it's very good to go abroad, but it has consequences. Okay. So as I say, when working on my PhD, I learned about the Schotter and Schotter bosonization treatment, which simplified Nozières de Domenici's X-ray stuff. And for the Kondo problem, it doesn't matter what dimension the fermions in the metal are. It's a point impurity, so one dimension is perfectly fine for that. So this is the one-dimensional bosonization, which some of you maybe, or hopefully, I'm not sure, I don't think most of you know it, but some of you do. So this actually came from Tomanaga's realization around 1950 that the particle-hole pairs in a 1D Fermi gas are completely represented by the RPA sound wave. So the speed of sound in a regular Galilean Fermi gas is the Fermi velocity divided by the square root of the dimension. But in one dimension, that's just equal to the Fermi velocity. And by looking at the spectrum, you see there are no particle-hole pairs which are low energy in the range of momenta between 0 and 2 kF, which of course there are in all higher dimensions. So he was able to represent the Fermi gas degrees of freedom by the harmonic oscillators of the sound wave. And so there we have it. We have a set of modes. It turns out, looking at this more closely, there's no harmonic oscillator with 0 momentum. So these are only kind of finite momentum harmonic oscillators. And more mysteriously in the Schotter and Schotter treatment, there's this formula which sort of represents the electron creation operator in terms of these harmonic oscillators. Kind of very puzzling thing at the time. How can you possibly represent the electrofermion creation operator in terms of harmonic oscillators? But there it was, okay. So this stuff had been worked out by my future colleague Elliot Lieb and Dan Mattis. I guess they were IBM or something at the time. And they corrected an incorrect solution of a beautiful model, the Luttinger model. Luttinger thought about simplifying the electron gas by kind of turning it into a Dirac model. And you just have a Fermi energy here, but you now, for 1D at least, you have the right movers and the left movers go down to -infinity. But he wrote this down, but he solved it. He didn't solve it properly. He missed an anomaly, a quantum anomaly, which this has, a chiral anomaly. And this was corrected by Elliot Lieb and Mattis. So I was interested in this because subsequently, Daniel Mattis applied these methods to the Wolf model. This other version, I was working on the Anderson model, but I knew the Wolf model was equivalent. And Daniel Mattis published his exact solution of the Wolf model, which I could see immediately was wrong, because obviously it was wrong because it disagreed with my work. And I was pretty kind of cocky about that, I guess. But I wanted to see, so I got interested in this because I wanted to see what exactly was going wrong with this bosonization treatment. It looked like a useful method. Why was it going wrong for this treatment of the supposed exact solution of the Wolf model? Okay. So remember the Nozières and the Dominicis were the people who did the X-ray edge problem. And Nozières was also working, he also worked, anyway, I met him first when he visited my advisor, Phil Anderson, and Phil was good about introducing his students to the visitors. So I had a chance to chat with Nozière, and he was pretty interested in this stuff. And the outcome of that was, later when I was thinking about postdoc positions, I got a very attractive offer for a 5-year postdoc in France at the Institut Laue-Langevin. And in fact, I also got after I'd accepted it, I was invited to Bell Labs, and he suggested a postdoc, and I found out, first I told him I'd accepted it, and I found out that that was a year when Jimmy Carter was president of the US, and I guess the left hadn't taken over in France. So there were 4 francs to the dollar, and my French salary was actually bigger than the Bell Labs salary. A few years later, when the governments had changed, there were 12 francs to the dollar, and it was a different story. But anyway, it was kind of surprising that I could turn down a Bell Labs postdoc for a better paying postdoc in France. Anyway, so whatever, went to France, and it turns out my office mate there was actually also interested in this Wolf model stuff. He believed in the solution, but anyway, so I started off investigating this seriously. Now, it turned out Matiss's error was a rather simple sort of error involving, you read that you treat the interaction as n up times n down. You throw away all the up and down terms because it's a single orbital, but the cutoff he implied broke the condition that it was a single orbital. So using just n up, n down as the interaction was breaking rotational symmetry. But a part of that, I realized that the fundamental thing missing in the bosonization form being used was there wasn't the operator to add charge to the system, right? So of course you've got an infinite Dirac seed, need something to kind of like an elevator going up from minus infinity to just push the charges up, and there's an actual angle variable for that. That was the missing ingredient. So finally, plugging all that stuff together, the formula became exact. 100% mathematically exact for the representation of so it's not completely in terms of bosons. These action angle variables provide the proper, and now from the modern viewpoint, I guess they're the primary fields or something like that, because no one knew about, this is before conformal field theory, at least, and so this is, things like the Virasoro algebra were not part of all this. Okay, so have an exact thing, so now we can play with it. And the interesting thing is, writing out the spectrum of a Hamiltonian, you now don't just have the sound wave velocity to play with. You've got the charge stiffness and the current stiffness, essentially the 1 over the effective mass or something. And naturally, the sound wave velocity is the square root of the two, but the ratio of the two is a dimensionless quantity that turned out to characterize the scaling dimensions of the various operators of this theory. And so this was a nice thing, and it could be applied to various models. And in particular, there are these nice beta ansatz models, which are exact. And so you can extract stuff from them, and okay. So the beta ansatz models, the first one is a spin half chain. So, but there's a young Hans Bethe, looking more kind of early on in his career than the older photos you find of him in his heyday. So in 1931, he went to Rome to work, had a postdoc with a fellowship from the Rockefeller Foundation. He first went to the Cavendish, and apparently he found out a waste of time because he spent his time working with or associated with Eddington, who had strange ideas about the fine structure constants. Then he went to work with Fermi, and he apparently said he regretted having gone to Cambridge. I told them that at Cambridge last week, actually, when I gave it. I mean, this history. But anyways, the beta ansatz models are, quote, exactly solvable, or they were at the time, because although you could get expressions for all the energy levels out of it, no one had any idea how you could possibly calculate any of the correlation functions. So they were a kind of partial solution. You could get exact information, but a lot of other exact information that you wanted was unavailable at that time. And so, okay. So with my work on, I was started off with the fermionic versions of Bethe models, chain, and I was able to see that the low energy structure of the exact solutions matched the Luttinger liquid theory that I developed, this just mapping things onto a Luttinger model with these few parameters. And a few cases, the exponents were indirectly known, such as when a perturbation opened up a gap, the way the gap opened up, you could work out what the scaling dimension was, and they agreed completely. So I realized I'd got a proper tool that actually allowed me to extract previously unknown information from these beta ansatz models. And this I called Luttinger liquid theory, because it was like Fermi liquid theory is to the free Fermi gas. This maps one-dimensional models to the Luttinger model. They call it, in Japan, it's now called Tomonaga Luttinger liquid theory. I guess maybe they thought I forgot about Tomonaga in naming it. Okay, and now because my institute was a neutron scattering facility, and the theorists were looked on a bit with suspicion as like parasites or something like that, it was good to have something to do with spin chains. And there was a lot of local interest in spin chains, it turned out. And there's a trick which works only for spin 1/2 chain that maps Bethe's model into a spinless fermion model, which immediately made the Luttinger model useful for looking at it from a new perspective. So in the mid-1970s, there was Luther and Peschel and others realized they could use this Jordan-Wigner transformation to turn the spin chains into a fermionic field theory. And this is using this old method dating from the 30s, the Jordan-Wigner transformation that maps spins into spinless fermions. A spin has two states, up and down. A spinless fermion the orbital can be empty or filled, and you can't put more than one. You can't raise the spin or more than once, and you can't add an electron. But of course, the spins on different sites commute, and the fermions anti-commute. So you need this kind of trick to order them in a certain way, so you can make the different spins anti-commute, and then you can map fermions to spins, or whichever way. So Bethe's solution of the spin half chain is actually a prime example of the dangerousness of mathematical physics results, which are, of course, assuming they're correct, they can be opaque. And in fact, Kosterlitz and Thouless got their prize or got their thing from realizing that the Mermin-Wagner exact theorem that says you can't have long-range order in a continuous order parameter in 2 dimensions at finite temperature was not a contradiction to having a phase transition at finite temperature, although superficially it might have been thought you can't have no order means you can't have a phase transition. The phase transition of Kosterlitz-Thouless is from a topologically disordered state to a topologically ordered state, not to an ordered state. But so people were interpreting the exact solution and saying, well, you experimentalists over there, stop bothering us with this nonsense. Our theorem rigorously proves you can't be seeing what you're seeing, right? This is a kind of bad attitude for theorists to have. But anyway, the experiments were clear there was a transition. Similarly, the beta ansatz was the people who wanted to use it. I just take the energy levels or whatever from the beta ansatz. They had no real idea how the stuff was calculated. And the people who were into the calculations really had not much idea about the physics. So there's a kind of discrepancy. And actually, it took about 60 years for this whole issue of the full underlying mathematical structure of the beta ansatz to be discovered. And it turned out it actually only reveals itself when you take an infinitely long chain. The finite size chain is slightly broken from symmetries that are only present in the infinite limit, but it was a kind of not understood at the time. It took a long, long time. Okay, so the isotropic Heisenberg model, this is the spectrum of the semi-classical large S spin chain. You've got a nice little sine curve here, and the correlation functions, because it's one dimension, they're actually not long-range ordered, but they fall off with for large S, they fall off with a very small power law. So they take a long, long time to decay, but they eventually decay. For the Bethe model, they have exactly the same spectrum, except for a constant, maybe the multiplying factor. The correlation functions were known had already been known, but by some symmetry argument that they fell off like exponent -1, so also algebraic. This one is this excitation, the bottom of the branch here is described mathematically as a hole in a one-string distribution, and this one is a semi-classical spin wave, so there's a kind of discontinuity between these two descriptions. And in fact, even earlier on, Phil Anderson, who wrote about the fact that the 1D model couldn't have true long-range order, and talked about broken symmetry, he has some comment. It seems like the only difference between if you plug S equals 1/2 into the spin wave theory, you're off by a factor of π/2 in the spin wave velocity. So there was kind of a belief that there was a kind of continuous connection between these two limits. And so, okay, so what the magnetism community felt about this was, since magnetism people love spin wave theory, right? So they think spin wave theory would be holding all the way down to S equals 1/2. There you will see it in the Bethe ansatz solution. So 1/S should be viewed as something like Planck's constant, a real number that can vary continuously as a measure of how quantum you are. S tends to infinity. There's no fluctuations anymore about the direction of the spin, and that's the classical limit. Actually, in doing that, no one had got around to comparing the specific heat, which was calculable from Bethe ansatz, with the thing. And if you actually plug in the correct value of the spin wave velocity or the linear speed from the exact Bethe ansatz, you actually find the specific heat is a factor of 1/2 what it's predicted from spin wave theory. So that people should not have been so complacent. I noticed that after the fact, but they hadn't noticed it. And late in the 1980s, it was shown this continuum has nothing to do with spin waves anyway. The excitations of the spin 1/2 system are pairs of topological objects called spin-ons, which carry spin 1/2. And now there's been plenty of neutron scattering of all this stuff. It's been very interesting since then. And of course, we can now know how to calculate things like neutron scattering cross sections. So Jordan Wigner converts the spin 1/2 chain into a fermion problem. That's great, so I can apply Luttinger liquid theory. So there it is. It's just hopping on a chain, and when it's purely easy plane, no SE, XY model only, no SE, SE term, it's even free fermions, right? So it's free fermions with a kind of interaction. And now it's also a half-filled band corresponding to zero field of the spin chain. And we notice that 2kF is half a Brillouin zone, so 4kF is a reciprocal vector of this problem. So Luce and Peschel converted this stuff into a field theory. The linear velocity terms just get converted here with linear slope. So this is actually just a kind of Luttinger model, just linearizing around the Fermi surface. And then they had the terms, well, backscattering terms where right scatters, no, this is just the interactions across I guess it's both backscattering and long wavelength interaction combined, because you can just flip. One will be right, left, left, right, the other will be right, left, right, left. But they didn't include any umklapp terms, which is two rights scattering to two lefts, which requires 4kF to be a vector. And that was thrown away, it wasn't thrown away in the Hubbard model, but where there was spin 1/2, but it was thrown away here because obviously spinless electrons, you can't write psi dagger squared. But in fact, although this was after the fact, I found they'd left out, okay, then you have to go a bit further, dig a bit more deeply, and you can now put a derivative operator in between the two. So the things are not exactly on the same place. And then you can have a thing, this lowers the scaling dimension of the effect, so it makes the umklapp weaker in effect, but it's still there. But I only found that after the fact. I didn't guess, I wasn't kind of I didn't think that. I did a numerical calculation. I calculated the correlation exponents of this model, which you could calculate analytically along the 0.5 line here, because the integral equations had infinite, were from minus infinity to infinity. Here you had to numerically solve some simple Fredholm equations and on the computer, and I plotted out the curves of constant correlation exponent, which take interesting values in various limits. But in particular, there was a whole lot of structure near the Heisenberg point, and it was immediately obvious to me, because I'd seen this, that this was a Kosterlitz-Thouless transition going on here. And of course, that it came from that Umklapp term that I had. So Luther and Peschel hadn't really got a proper idea. They didn't fully understand why the gap opened up at the Ising transition. If you looked at the bosonization form, there was something not quite right around K, around zero momentum. So there was something called an infrared cutoff was being used, and some spurious detail of their infrared cutoff confused them. And in fact, the Luther and Scalapino had an alternative theory to Kosterlitz-Thouless for the XY model by doing the quantum mapping the other way. They felt that Kosterlitz and Thouless were wrong because it disagreed with their incorrect assumptions about what happened in the chain. But in fact, Kosterlitz-Thouless, of course, were correct. Anyway, so the thing was, it was a double vortex transition that was happening, and not a single vortex transition. A single vortex transition goes to a unique state, a double vortex transition goes to a twofold degenerate state, and indeed, the easy axis limit, the Ising case, is a twofold degenerate state. And these are various calculations I did at the time and drew with pen on a nice drawing kit I had. Okay, so the topological transition in Kosterlitz-Thouless transition occurs in 2 dimensions at finite temperature, but we do this Wick rotation that maps you from classical stat mech to quantum mechanics in 1 + 1 dimension. But in classical stat mech, the Boltzmann weight is always a positive quantity. It turns into some kind of transition amplitude in the quantum problem, but those can either be positive, they can be real, positive, or negative, or complex. So the quantum versions of these classical problems are richer than the classical problem because of this feature that you're not restricted to positive weight transition factors. So what's actually happening in the Kosterlitz-Thouless transition? This is standard. Okay, this would be a transition. This would be a standard Kosterlitz single vortex transition from winding number 1. From winding number 0 to winding number 1, the vortex now is a point in space-time, and the center of the vortex is the center of the tunneling event. If you look closely, you'll see that at the center of the tunneling event, the spins on 2 neighboring sites are parallel to each other. They're never parallel to each other at any other point in the history, and then asymptotically, they want to be staggered up, down, on neighboring sites. And this is a transition, this is a transition from winding number 1 going here and winding number 0 below and winding number 1. So if I go in a loop and count the winding as I go around it, I've got a vortex in the middle. So in quantum mechanics, the vortex turns into a winding number tunneling event. Now let's look more closely at that. The vortex happens on a bond. The tunneling is centered on a bond. And looking at that place where the thing has all the spins to the left, rotate 180 degrees anti-clockwise, at least the ones nearby the vortex event, and the others rotate 180 degrees clockwise. So if the bonds are all equal and I move this from one bond to the next bond, the difference in the 2 path amplitudes is just one spin that used to rotate 180 degrees to the left in the easy plane rotates 180 degrees to the right. So the difference between the 2 is a single spin rotating 360 degrees. But if that's spin a half, that gives you a -1 factor. So there's a quantum interference event between the vortex tunnelings on neighboring bonds if it's half-integer spin. And that was why only the single vortex process is cancelled by quantum interference. So this became clear from this that there was the progression from easy plane to easy axis is quite different between integer and half-integer spins. in half-integer spins, you get this, which is the first thing that I invented, looked at, was the, you get a double vortex transition from the easy plane gapless state to a doubly degenerate state, because it only changes the winding number by 2. So the two massive sectors are even and odd winding number, basically, or were. And in the integer case, and the critical exponent is 1, because the out of plane and here, the critical exponent is a quarter, because it goes up by a factor of 4 when you go to double the vortices. So here it was clear the transition happened well before you got to an isotropic situation and you went to a non-degenerate gap state. Coming from the other end, from the Ising end, you also hit an Ising transition before you hit the point. So there's a sandwiched region of what turns out to be topological state. So I was very shocked. I didn't expect to find that. I just worked out what happens for the spin half case. I said, well, this Luttinger liquid method works for spins. Let me just do it for spin 1. And then immediately there's a selection rule. It turns out that if you unwind the twist at half filling or zero field, if you untwist by 1, it changes the momentum by 2 pi s. So if s is half integer, it changes it by pi. So you can't possibly, from the Hamiltonian viewpoint, you can't have a tunneling which changes the winding number by 1, because momentum conservation or crystal momentum conservation rules it out. Well, there's no such selection rule for the integer spin. Yeah, so I was totally shocked, but it told me that the conventional wisdom was 100% wrong. You know, it's not often you see that, but that's who it was. There's probably other examples out there waiting for you guys to find. Now, the magnetism community didn't really react in a very nice way to this, I have to say. I mean, I gave things like a talk at some meeting, and a senior person who I won't mention, although they're dead now, I guess, kind of stood up and said, this is complete nonsense. There was our young postdoc, right? This guy stands up and says, this is bullshit, basically. You know, didn't use that word. Right, so, the referee reports were equally kind of thing. I remember statements like manifest contradiction with fundamental principles such as renormalizability and continuity, etc. Very pontificating statements about this is nonsense, right? But anyway, it turned out not to be nonsense. And this gap phase, this little window turned out to be essentially one of the first examples of topological quantum matter, which is why it's become interesting. It's a large window for spin 1, but it gets smaller and smaller, very small for spin 2 and spin 3. And this is actually now called a symmetry-protected topological phase, with time reversal and spatial inversion protecting it. So this paper, my original preprint on this from France was rejected 3 times, you know. Physical review letters, okay, I can't remember the second one. Finally sent it to Zeitschrift für Physik, and they rejected it too. It was probably the same, maybe it went to the same referees, I don't know. But in any case, I really clearly wasn't explaining the thing in a clear enough way. Although the original reprint was lost, but it was widely circulated, so Colloquium had one, and one was tracked down, so I've actually retyped it and put it on the archive. And I read it, and I think it's perfectly clearly explained. It certainly doesn't say anything about conjecture, which is the thing was written off. This was Haldane's conjecture, and many mathematicians are still trying to prove Haldane's conjecture again, because they like to prove conjectures. But it was a pretty good prediction, I thought. Anyway, there you go. I'm still a bit kind of annoyed about it 40 years later, but it was extremely good for my career, because all these people having said this stuff was wrong, you know, and then it turning out to be right, you know, was a big plus. I mean, either I was a genius or they were idiots, so they decided to kind of say this was, you know, whatever. So the later developments on this were the development of a topological term. Obviously I didn't fully understand a lot of the things, and then also the AKLT model, which was future colleagues at Princeton found a matrix product state, a simple one which exhibited these things. And So that helped things clear. So in heavier atoms, we see that a group of electrons in atomic orbitals you fill up a d orbital, they all go in parallel. So the total spin, of course, is an integer multiple of a half, basically. And so spin is quantized. Now, this was the discovery was before Berry's phase. So, but a couple of years later, Berry found his Berry phase, and that started to lead some kind of intellectual more justification to this argument. So Berry's phase and the Chern number, etc., show that obviously it's incorrect to think of 1 over s as a continuously variable parameter. 2s has to be an integer for Berry's phase to work. It's only if the spins only fluctuate in a narrow cone around some fixed axis that you can forget about the quantization. Once they ever go on paths which vary over large distances, you cannot say S is continuous. Okay. So conventional magnetic order has, the spins are just lined up. In the antiferromagnet, they kind of line up anti-parallel. And so it's easy to formulate a spin wave, a field theory of this. So taking a continuum picture, you've got the angular momentum density of the spin, which is the long wavelength part, and then the momentum pi part is the order parameter of the Néel state, and they're orthogonal. So you end up with a Hamiltonian rather straightforwardly, which I recognize to be the nonlinear sigma model, the O3 nonlinear sigma model. And so the issue was how to explain that this thing seemed to have 2 different quantizations, one with a gap for integer spin and one without a gap for half integer spin in the field theory language. And this is and of course, working backwards from the Hamiltonian, I arrived at the action, which is the nonlinear sigma model action. And it's just a simple spin field, a unit length spin field, a one-dimensional Lorentz invariant, etc., with a constraint. But so I was worrying about, this different thing. Was it CP1 versus O3 or whatever? But in 1983, I visited Princeton and I explained, and I buttonholed Ed Witten, and I told him I've got this problem with this field theory that seems to have 2 different ways to be quantized. And he said, "Oh, don't you know about the theta term?" And I said, "What's that?" And he said, "Okay." So I found out about the so-called theta term that you can add to the action, which is linear in the time derivative. And this breaks time reversal invariance unless e to the I theta is equal to plus or minus 1, because of course it occurs exponentiated in the path integral. And with a direct lattice, using Berry's phase, immediately it became clear that theta was 2 pi s and the issue was resolved. So this was actually the first occurrence of the theta term in condensed matter. This occurred some other times, right? And so the realization that the action could have a topological term which was linear in time derivatives that disappeared when you formed the Hamiltonian was actually something that we didn't know, we weren't really aware of very much, because people didn't use actions at all, they used Hamiltonians. And this actually was probably marked the first time condensed matter theorists started theorist use of the action as opposed to the Hamiltonian. And finally, my paper got accepted when written in terms of the nonlinear sigma model, as opposed to the original version written in terms of quantum Kosterlitz-Thouless. So this is, of course, how you lose the action. If I have an action which has got a term linear in time derivative, quadratic in time derivative, and 0, when I form the standard Hamiltonian, you see I reverse the sign of the one without the time derivative. I keep the one which is quadratic, and I lose the linear one. So but it shows up, its effect shows up in selection rules such as the quantum number, the momentum associated with a twist being pi and one being 2 pi s, right? Okay, so while this was all happening, people actually did discover a beta ansatz model with spin 1 that actually looked gapless, kind of like the original beta ansatz model. It actually was one my Luttinger liquid theory was puzzling on. It didn't give me any proper results, and that's because this was actually a non-abelian conformal field theory, which Luttinger liquid theory is really an abelian one. But in any case, I didn't lose sleep of it. I knew within 10 minutes That was a different model, and I was pretty confident that my results were basically correct. And indeed, there you see this extra term biquadratic exchange puts in, and luckily the AKLT model is in, also includes the biquadratic term, but it was in the holding gap region. Okay, so what's entanglement? So going back to why this happened, the original state was, you just line up the magnetism was just lining up ordered atoms, right? No quantum entanglement between them, essentially. Well, the new state essentially has you split these spin ones into two halves and combine them with their neighbors, and you have entanglement that way, and you get left with these free 1/2s at the end of the thing, which is very typical of topology. No one really, in magnetism community, possibly Phil Anderson had thought about resonant valence bond state earlier in the 70s, 75 or something like that, with Patrick Fazekas. But anyway, no one in the magnetism community kind of thought about entanglement or topology, so it's kind of, it's retrospect. Of course, they didn't really adapt to this very easily. But in science, we're not going to have a religious argument about metaphysics. You do an experiment. And indeed, clever material scientists started making spin-1 chains like this NEMP chain. And my neutron scattering colleagues died out on this for years afterwards because they were doing neutrons. They were competing between Grenoble and Chalk River. And anyway, the gap was seen. And this shows that, materials, actually having an experiment is a way to answer questions. And that's the remarkable thing we have in condensed matter, which I guess the string theorists don't have going for them, right? And the controversy has actually been very powerful in motivating people. A number of tremendously good techniques, the DMRG, Steve White really tested out his DMRG method on this problem. And then matrix product states came out of it. Experimental stuff like these chains came out. So actually a controversy is incredibly good for science because it gets people interested. And, an experimentalist, the most satisfying thing is to prove some dumb theorist wrong. Well, the second best is okay too if they prove some theory right. In either way, it's good for us all. Okay, and the meme of this is for the, if people hold hands and get entangled, even though you think hands should come in pairs, unless you've had an accident, then you get left with two unpaired hands at either end of this chain, and this is like the hydrogen atom of topological states, apparently. And there's my prize certificate. And they actually put the AKLT model on it, but who's counting, I guess. Very lucky that LIGO, the press when it came out, they were saying, huh, what's this? Because they were all expecting LIGO to get the prize that year for the gravitational waves, but I guess the event was only announced after the Jan 31 deadline, so. Okay, and just a quick thing on that, there's current to get current. The Majorana, there's a lot of interest in possible Majorana quantum computing, or even, of course, even better would be Fibonacci, but Microsoft have been working on this. If I put a spin orbit coupled nanowire, which basically makes it kind of spinless in contact with a superconductor, I can get something interesting happening. I can always formally rewrite an electron creation operator. I guess I should go back one. Oops. You notice the putting the things underneath the superconductor kind of removes the electric charge from the electrons nearby. They all migrate, the charge migrates to the surface of the superconductor. So in the neighborhood of the superconductor, the electrons aren't really carrying charge anymore because it goes around on the outside of the superconductor. And so then if I can formally write the creation operator, take its real and imaginary parts as two Majoranas, you can make a completely formal split. That's doing nothing, but it turns out that in this superconducting arrangement, the system can rearrange itself by coupling with a superconductor, which has got a p-wave character, and to reorganize itself to leave half an orbital, half an electron orbital, or a Majorana zero mode at either end of the chain. Of course, that's the idea behind the Majorana 1 let me call it a quantum computing architecture, because I'm not totally sure about the actual hardware, whether it's working or not. Okay, a little bit time left. So surprise number 3, zero field anomalous quantum Hall effect and topological insulators. This was also a surprise. How did I get into this? In late 1986, the following paper was published. It was a paper by Fradkin and co-authors. They call it Physical Realization of the Parity Anomaly, etc. They took a model with spin-orbit coupling. And at the end of the day, they somehow ended up with a quantum Hall effect and in zero magnetic fields. But they seem to think you could get that out of spin-orbit coupling. So I was very interested to read this paper. I mean, knew a bit about some of this stuff, but not very much. But I was convinced it had to be wrong, because you need the chiral edge states going one way for the quantum Hall, and that clearly indicates broken time reversal invariance. So even if I can get rid of the magnetic field, I cannot get rid of the time reversal invariance. And of course, spin-orbit coupling puts complex numbers into your calculation. So it's likely there was some algebraic error in that paper which accidentally broke time reversal. But I couldn't track it down, so I submitted a comment to Physical Review Letters along the lines that you can't possibly, even if you can get zero magnetic field quantum Hall, you can't possibly get it without broken time reversal, right? So, of course, comment response is a very kind of almost useless thing, because each party is doesn't understand a word of what the other one is saying, and they're talking at cross purposes. And really, it's not that great a deal to tell you someone else's paper's wrong, right? It's not very nice, really. But they actually, their paper, reminded me about the work of Semenoff on Dirac equation in graphene, which was then called single graphite monolayer, because it was a theorist's material, not a real one. And okay, so I thought, look at that model and see if I could come up with a model to put into this dialogue to show that you needed time reversal invariance. And yes, I found it. And then I realized this is a lot more interesting than saying Fradkin's paper's wrong, right? This is really interesting that you can get a zero field quantum Hall effect. And there it was. That was the birth of that model. If I hadn't noticed the paper of Fradkin, I would not have got into this business, and I would not have come up with this very cute model, which turns out to be it basically uses ferromagnetism to get quantum Hall. I viewed it as putting a magnetic dipole pointing out of the plane at the center of each of these hexagons, and the magnetic field of that dipole doesn't give any net magnetic flux through the plane, but gives you these second neighbor hoppings. Okay, so it was interesting to see let's just quickly look at it to actually see how it works. If I take graphene, it's got an edge state, or some edges have an edge state. The zigzag edge has one, where the Dirac points touch, and there's a edge state which occupies, I think, 1/3 of the band that joins the two Dirac points. I open a gap by either breaking inversion or time reversal, and so when the gap opens, each end of the edge state has to decide which band it wants to stick to, right? So if I do it in the boring way, which was actually Semenoff's way, which was the breaking inversion symmetry, then both ends are attached to the same band. But if you do it the other way around, I get a quantum Hall edge state. So it was very surprising at the time, but it should have been there before. This took a long time to be experimentally realized, but let's not go through that. It also led to this model has been very fruitful. It was very useful in proving all kinds of stuff about, ferromagnetic edge states, and then it led to topological insulators, where Kane and Millie took 2 copies of it. I'd also thought about doing that, but I always thought, well, once you switched on the more spin-orbit coupling that broke conservation of the 2 spins separately, it would open up a gap. I never bothered to do the calculation to find out. Kane and Millie wondered what would happen, and they put it on the computer, and they found out that this new Z2 principle of Kramer's degeneracy protected it. And then that led them to find the 3D quantum topological insulators and it also led to topological photonics, which Sri Raghu worked with me on. And more recently, now fractionally filling of this thing has led to, with band flattening. So by choosing the second neighbor hopping appropriately, I can flatten one of the bands to be quite narrow. And it turns out in this system with nearest neighbor coupling, you get a fractional quantum Hall state. Okay. So it's actually been an incredibly useful thing. That was Shamon and Al found that. And this shows that actually some of the most interesting discoveries are like surprises to everyone who participated in them. They occur because you somehow stumbled, your research path somehow stumbled into the path of this remarkable thing waiting to be discovered. And these surprises, you know, they change our thinking, right? I mean, look at we never used actions before in the condensed matter, you know, before the theta term came out and stuff like that. Loftin's wave function has a very interesting history behind it. I don't have time to tell it, and it would be a second-hand account, so you should get him to tell it to you. But it's also a surprise, okay? As you might expect, it's not something that he was expecting to find either. So finally, let me terminate. Let me just finish off with this motivational message for all the student audiences. My message is that, you know, when you're starting a career in science, anyone has pretty well tiny chance, but anyone working in basic science has the chance that they may end up with a Nobel Prize, not because they were a fantastic genius like Einstein. There's actually plenty of fantastic geniuses around the place, but by the luck to stumble across something that truly unexpected, that no one expected to be there, and later turns out to have a fantastic impact on the field. Of course, to do that, you do need a proper preparation. You actually need to be able to recognize that something is interesting, and you probably need to actually be able to prepare to fight for it and have commitment to push it through, right? And actually, these kind of words are exactly the same kind of words you hear at a business school commencement address, because to succeed in business, you need luck, preparation, and commitment. So I guess it's a life lesson for you all. Thank you.
Thanks very much for that sort of personal journey that you shared with us. And I'm sure people have questions. So yes, sir.
The gap. And what's the question? Yeah.
Yeah. So when was it realized and by whom that there are no gapless fermions at any order of a 1/s expansion?
Well, they're not really fermions, but there was, I don't know if people looked at it. I don't think people have studied the spin chain from the 1/s expansion. Or maybe they have, but of course, you won't really see it in 1/s. It doesn't have presumably doesn't have a proper expansion in 1/s. I guess that's the thing, right? What you're doing is you divide the spin by s, and then you have a unit vector field and write down the commutation relations of that.
Or even
it's tunneling. Basically, you do some kind of what perturbation expansions miss is tunneling. Okay, what's actually going on here is in the semi-classical case, if you have an easy plane system, I have a better version of it for the isotropic case. In the easy plane system, the winding number of the order parameter is classically conserved, and so you actually have to break the order parameter apart at one site, and then you can rejoin it again. If you're too isotropic, there's also another competing mode where you can stay near each other, but go over the North Pole or over the South Pole. And then you find the difference between the two is taking the spin chain all the way around, which gives you a Chern number, and it's the same interference effect. So these are effects I don't think you pick up tunneling effects in perturbation theory. That's the issue, because they're not present to any order in the expansion parameter. So the gap will be exponentially small as s goes to infinity, probably like exponential of 1 over s, right?
Is it possible to move the theta parameters, and has been done any experiment on that?
Yeah, the theta parameter is shifted. The theta parameter is shifted by making the bonds, breaking the dimerizing the bonds. And yes, you can tune it. The symmetry depended, the cancellation depended on everything being unchanged when you move the tunneling point by one thing. The theta is affected by changing the bonds, which breaks the inversion symmetry. Something very similar happens in the topological insulators. There's a theta interpretation. There's a quantum Hall effect on the surface, or there's a plus or minus. There's a gapless state with a Dirac mode on the surface, but a little bit of magnetism pushes it either one way or the other way. And again, by putting magneto, that's present in the absence of the other kinds of non-topological magnetoelastic electric coupling. So you have a magnetoelectric material. It's like it pushes the theta parameter away from 0 or pi. And I think people have been interested in that kind of stuff experimentally. There's quite a lot of work on magnetoelectricity.
Let me ask sort of a general question. Since you mentioned about how controversies are very fruitful often, do you see any controversies in contemporary condensed matter physics which might be fruitful, especially for young people to kind of think about? And
I don't know. I mean, no one's fighting about something. I mean, ITC people were fighting over, but I mean, there's no clear controversy there because it's an unclear mess. But I don't know if a Stanford view might be different, but you might know about it from the colleagues. But yeah, I think understanding the Majorana stuff better. I mean, Leggett just kind of worries about reality of Majoranas, but I don't know. I think I don't see an immediate kind of big controversy, but when it comes up, you'll know what it is, right? There'll be people shouting and screaming on either side of it.
Some controversy about what is the correct explanation for the normal state of ITC?
Okay. Oh yeah.
Still argue.
Oh yeah. The famous. Yeah. Okay. The strange liquid, or strange metal. Strange metal. That's right. There was all this. It's still controversial. Yeah.
So you mentioned about the two different quantization of the sigma model. So there were these commensurability theorems like the Lipschutz-Matisse theorem, which already suggested that there could be different quantization because of
I guess that, at the time, the Lipschutz-Matisse was very specifically attached to that spin-half business, right? The spin-half chain. It was much more parochial, I guess. Whether Lipschutz-Matisse, I mean, Lipschutz-Matisse, I guess, would be talking about, in its most general form, a crystalline material with a half-integer or integer spin in the unit cell. But I guess this is, of course, has a unit cell. I don't know. It wasn't kind of a issue at the time. The magnetism people certainly weren't onto it, right? They thought this stuff was so crazy. How could there be a difference between? And then, of course, this again, mathematical physics is powerful, but it can be misused, right? I mean, in a sense that there could be another interpretation. Just because the result's exact doesn't mean you're interpreting it correctly in the right context. Yeah.
Okay, if there are no further questions, let's thank Duncan again.
Thank you. Very much. Yeah.